Bismillah ar-Rahman ar-Rahim. Today we're going to talk about lecture 5 of chapter 21, electric charge and electric field, and we will discuss in this lecture the electric dipole. In this lecture, as usual, we will discuss the properties of the electric dipole. We will study the electric field produced by an electric dipole. We will study the force, the torque on the electric dipole in the presence of uniform electric field. And finally, we will study the potential energy of the dipole in the uniform electric field. What is the definition of the electric dipole? An electric dipole is a pair of point charges having an equal but opposite sign and separated by a distance c. Let's see this configuration. So let's repeat the definition of the electric dipole. I said the electric dipole consists of two charges. One is positive, the second is negative. They have the same magnitude, but separated by a distance d. So in this configuration, as you see here, we have negative charge, positive charge, separated by distance d. This is minus q, this is q. They have the same magnitude q. In this case, we call this configuration electric dipole. The electric dipole moment now. The electric dipole moment is defined as a vector directed from the negative charge to the positive charge and having a magnitude q multiplied by d. So this is our vector p, which is equal q multiplied by d. This is as vector. It's pointing from the negative charge to the positive charge. What about the magnitude of this electric dipole moment? It's q multiplied by d. D is distance in meter, q in coulomb. So the electric dipole moment, it's a coulomb meter. Good. Let's continue. Now we want to calculate the electric field due to this electric dipole on a point P along the y-axis. The electric dipole is along the x-axis. The question said an electric dipole consists of positive charge and negative q, plus q and minus q, separated by distance d. This distance d is equal to a. The question is, find the electric field along the y-axis at the point P, which is a distance y from the origin. And we will assume that y is greater than a. As usual, we want to draw the situation again, and we want to solve step by step. We want to draw the free body diagram, and then the forces, and then the electric fields. This is our positive charge q. This is our negative charge minus q. This is our x-axis. And the y-axis is here. This is our y-axis. What is our point P? The point P is along the y-axis. As you know, positive charge produces an electric field outward. Let's say this is E1. Negative charge produces an electric field inward. E2. The sum of these two electric fields is the following, using the parallelogram method. This is E at the point P. Okay, so according to the superposition principle, E at the point P is equal E1 plus E2. Good. So you see here that the vector E1 and E2 both have X and Y components. What do you think about the Y component of these two vectors? Let's draw the Y component of the vector E1. This is E1Y. What do you think about E2Y? This is E2Y. What do you think about the distance between the two, between the charge, the positive charge at the point P and the negative charge at the point P? It's the same. Let's say this is distance R. What about the magnitude? The magnitude is the same for the two charges because it's an electric dipole. Now, the E1Y points upward with a positive Y, E2Y points downward with a negative Y. So we will write due to the symmetry of the problem. What we can conclude due to the symmetry, EPY which is equal E1y plus E2y. This is how much? Yes, good. It's 0 due to the symmetry. One is pointing upward, one is pointing downward. They have the same magnitude, so their sum is 0. So only we have an x component. EP is equal E1x plus E2x. Okay. Now the question, what do you think about E1 and E2x along the x component of these two vectors? The same thing, we have the same distance, we have the same angle here. Let's say this is our angle theta, let's say this is our angle theta, and also theta is here, theta is here. So the same angle, the same distance, the same magnitude of charge. So these two components are equal. So let's write here 2E1x. So the question, what is E1x? According to the definition of the vector of the x component, so it will be E multiplied E1 in magnitude multiplied by cosine theta. Okay, so this is the total vector of the point P. It's 2 multiplied by E1 KQ over R squared multiplied by cosine theta. Cosine theta, as you know, the cosine is the adjacent of the angle divided by the hypotenuse. What is the adjacent of this angle? The adjacent of this angle is A. Here we have the right angle. Okay. And what is the hypotenuse? It's the vector, is the distance R. Now, the question comes back to the R, where R equal what? Equal A squared plus Y squared power 1 over 2. That means square root. Yes, good. Good. So now EP equal 2KQA divided by R power 3. That means cube. That means A squared plus Y squared power 3 over 2. Good. So this is our vector. Let's write here as vector, and here we will add the unit vector because it's along the x-axis. Okay, now the question. We said in the question that y is too much big. It's too much big compared to the a. So what we're going to do for the a will be neglected. We neglect a. Then also, what do you think about the moment dipole? The moment dipole is q multiplied by d, and d in our case is the distance from minus q to positive q. So that means it's 2a and q. So this equation becomes as the following. Let's take another color. So E at the point P, it will be 2KQA. That means K multiplied by P, and we neglect the A. That means divided by Y cube and along the x-axis. So this is the final expression of our electric field at the point P produced by the electric dipole. The electric dipole is along the x-axis, and the point is along the y-axis. And we are done with this first example. Now let's move to another example. An electric dipole is centered at the origin with P in the direction of the positive y-axis. That means the negative charge is in the negative y, and the positive charge is in the positive y, according to this. The question derives an approximate expression for the electric field at the point P on the y-axis for which y is much larger than d. Y is much larger than d. Good. To do this, use the binomial expansion valid for x smaller than 1, the magnitude of x is smaller than 1. We will do the same steps. Just I will go through this equation. The same thing, we will say that the electric dipole at the moment, the electric field at the moment P is the sum of E plus E minus. E at the point P is E plus E minus, or E1 plus E2. Good. Here we have only the y-axis. We don't have x component. We have all the vectors on the long y. So at first, we will try to calculate, to write the expression of E plus and then the expression of E minus. For E plus, it's kq over r squared, and r is the distance from q to the point P, which is equal y minus d over 2, y minus d over 2 squared. The second vector kq over r squared, r is the distance from the negative charge to the point P, which is equal y plus d over 2. So it's minus 1 plus y plus d over 2 squared. Now the question, we can write this equation in order to use this binomial expansion. So 1 over y minus d over 2 squared, it will be 1 minus d over 2y power minus 2. Okay? Let me explain step by step. Okay. As I said, the electric field at the point P is E plus E minus. It's along the y-axis only. Okay, now the question, what is this and what is this? So let's write EP equal. For the first vector, it's KQ over, let's write E plus squared plus K minus Q over R minus squared. So it will be KQ factor of 1 over R plus squared minus 1 over R minus squared. Okay, good. Now the question, what is R plus and R minus? R plus, according to the figure, it's K, let's write the vector KQ factor of 1 over, we said it's y minus d over 2 power 2 minus 1 over y plus d over 2 power 2. Yes. So this is equivalent to KQ factor of y minus d over 2 minus 2 minus y plus d over 2 power minus 2. Good. Okay, now we will use the binomial expansion. What is the binomial expansion that we will use? 1 plus x, when x is very small, power n, it will be 1 plus n x, 1 plus n x. So let's write here. It will be KQ factor of, at first we have to write this y out to get 1 plus x power n. So it will be okay. So what we're gonna do, we will factorize in terms of y. So it will be divided by y squared multiplied by 1 minus d over 2y power minus 2 minus the same thing, 1 plus d over 2y power minus 2. And like that, we got this, this binomial expansion. In this case, what we're going to do, what we're going to write, so it will be kq over y squared multiplied by 1 minus minus 2 d over 2y minus 1 plus d, okay, so here what do you have? We have minus 2 also. Minus 2 d over 2y. What we're going to do for this 1 and 1, They will be cancelled. Negative sign and negative sign. 2 and 2. 2 and 2. So the result would be, what will be our result? And here also the minus and the minus. Our result would be KQ over y squared multiplied by what? D over y. So 2D over y. So the result would be over y cubed. Yes, good. So the result would be over y cubed. What do you think about 2dq? It's 2dq is only p. And in this case, what we're gonna get? So the electric field at the point P will be K P over y power 3, and it's along the y-axis. Good. And like that, we are done. Yeah, you see that it's as a function of okay, so wait, it's not 2qd, it's let's write the 2 over here, and it will be multiplied by 2, because in our case P is qd, not q2d, qd only. Okay, and we are done. Okay, now let's talk about the torque. Suppose that the electric dipole is placed in the external uniform electric field E. Now we have positive and negative charges with the same magnitude separated by distance d in the presence of an external electric field. The electric force acting on the two charges are given as, this is the positive charge plus Q. The electric force is related to the electric field by the following equation, QE. If Q is positive, the electric field and the force are in the same direction, so as we have here. If the Q is negative, the electric force is opposite in the direction to the electric field. So now, the net electric force acting on the dipole in the presence of a uniform electric field, it will be QE plus minus QE. QE minus QE, so it's 0. We can say that the net force on electric dipole in the presence of uniform external electric field. This is the condition. In the presence of an external electric field, so how is it? It's equal to 0. Okay, now let's move to the torque. Let's assume that the dipole moment P makes an angle phi with the electric field E. So this is our electric field E, and this is our moment dipole P. And this is our angle phi between the two vectors. The two torques, the first one exerts a torque, the second one exerts a torque also. The two torques have the same magnitude, which is equal QE multiplied by d over 2 sine theta. Okay, so what will be the total torque? The total torque is only the sum. The total torque, it will be P multiplied by E multiplied by sine theta. Okay, where P is QD. QD is E. QD. So after that, we can realize that the torque is only P cross E. Okay, the moment dipole P cross the electric field E. What is the magnitude of this torque? The magnitude of this torque is PE sine theta. But please, you have to be careful about the theta, as phi is the angle between P and E. It's convenient to express the torque in the vector form to be P cross E. And like that, we are done with the torque. Let's move to the work and the potential energy. To calculate the potential energy of the system, we need to calculate the work required to rotate the dipole through an angle phi with respect to the dipole center. As you know, the torque tends to decrease phi. The work to rotate the dipole through an angle d phi is equal dw equal minus tau d phi, where tau is Pe sine phi. So after integration, W, the work, it will be minus the integral from phi initial to phi final, tau d phi. After some steps, it will be what? It will be minus Pe. The primitive of sine, it's minus cosine phi. From phi initial to phi final. This is the expression of the work. And we have negative sign, then we cancel it. From the work, we can get the potential energy as the change of the potential energy is equal to the negative of the work, to the equals negative the work. So delta U equal U final minus U initial equal minus W. And it will be the following. After some steps, the difference of the potential energy is minus Pe cosine phi final minus phi initial. But it's convenient to suppose that phi initial is 90, so cosine phi initial is 0, so we can set it there. In this case, we will talk about the general expression of the potential energy for the torque. It will be minus Pe cosine theta. So Pe cosine theta, it's the dot product between P and T. So we can say that the potential energy is minus P dot E. Let's make a summary here before we start some examples. Okay. For the net force of an electric dipole in the presence of an external uniform electric field is 0. And we have to underline in the presence of uniform electric field. This is only valid when we have a uniform electric field. Okay, the second point, the torque tau is equal P cross E. Okay, so in magnitude, it will be P times E times sine phi, and phi is the angle between P and E. For the potential energy U, it's minus P dot E. Okay, in magnitude, it's equal, the potential energy is Pe cosine phi. Okay. And the same equation can be minus Pe cosine phi U, because it's scalar product. The magnitude of the torque, of the potential energy is the following. Okay, now let's move to some examples. Example 2113, force and torque on a dipole. Let's consider a dipole in uniform electric field with a magnitude 5 times 10 power 5 Newton per coulomb. The two charges are of magnitude 1.6 times 10 power negative 19 and separated by a distance d, which is equal 125 nanometer. Question A, Find the net force exerted by the field of the dipole. At first, what do we have about the field? The field is uniform, and we have electric dipole. So the force is directly equal to 0. Okay? The second question, the magnitude and the direction of the electric dipole moment, P. The magnitude and the direction of the electric dipole moment, P, is equal Q multiplied by the distance, points from negative charge to the positive charge. Let's start by the magnitude. Q multiplied by D. Q is 1.6 times 10 power negative 19. The distance is 0.125 nanometer. We multiply both. The product between them gives 2 times 10 power negative 29 coulomb meter. What about the direction? This is our P, okay? And with the x-axis or with the electric field makes an angle 145. This vector makes an angle 145, and it's clockwise. So it's 145 clockwise. If we want to calculate counterclockwise, we see here that it's 180 plus 35. 180 plus 35 counterclockwise. Okay, so the direction of P is from the negative to the positive charge. So 145 clockwise from the electric field direction, or 215 degree counterclockwise. Okay, the third question said, what is the magnitude and the direction of the torque? As you know in the summary, and as I give you in the summary, the torque is P cross E. So the magnitude is PE sine phi. So let's write here PE sine phi. So it would be 5.7 times 10 power negative 25 Newton meter. Using the right hand rule, we can get the direction of this torque. What is the right hand rule? Point your fingers in the direction of the first vector, which is P. Curl your fingers to the direction of E, and your thumb of your right hand points outward, so out of the page. This corresponds to counterclockwise torque. So the torque is counterclockwise, or we can say only it's out of the page. Now the potential energy. The potential energy, as I said, it's minus PE, which is equal minus PE cosine phi. Okay, so P is 2 times 10 power negative 29 for the previous question. E is 5 times 10 power 5, and phi is 145. So we got the potential energy to be 8.2 times 10 power negative 28 joule. The charge magnitude, the distance between charges, the dipole moment, and the magnitude of the torque and the potential energy are all very small, but are all typical of molecule. Okay, so the joule is a very big unit for the energy, for the potential energy due to the electric dipole. So usually we will use the electron volt. Okay, no problem with that. Now let's talk about the water molecule. The electric dipole moment of water molecule is 6.3 times 10 power negative 30 coulomb meter. A sample contains 10 power 21 water molecule with the dipole moments all oriented in the direction of an electric field of a magnitude 2.5 times 10 power negative times 10 power 5 Newton per coulomb. The question is, how much work is required to rotate the dipole from this orientation, Q equals 0, from this orientation, phi equals 0, not Q, or theta equals 0, to one in which all the dipole moments are perpendicular to the field, that means theta equals 90. As you know, the external work is asking about work, how much work. The work is related to the electric dipole by delta U with a negative sign. Here, the work is required, so we will write the external work is equal to the potential difference, to the difference of the potential energy, and it will be equal minus PE cosine phi final minus phi initial. Phi initial, how much we said? We said it's 0. Phi final, we said it's 90. and we have P, and we have E. This is for how many molecule? This is only for one molecule, okay? So it's only for one molecule. For one dipole, we have W external, the external work, it's P, how much P? 6.3 times 10 power negative 30, multiplied by E, 2.5 times 10 power 5, and we will get the result for one dipole. 1.6 times 10 power negative 24 joule. Now, how many molecule we have? We have 10 power 21 water molecule. So the work required to rotate one dipole will be multiplied by the total number of the dipoles or of the molecules. For all dipoles, the total work becomes the external total work is 10 power 21 multiplied by 1.6 times 10 power negative 24 joule. And we got the result, the external total work required to rotate the dipole from theta 0, theta equal 0 to theta equal 90. It's 1.6 times 10 power negative 3 joule. But here I have something to highlight. These calculations are only valid when all the moment dipole are oriented in the direction of an electric field. That means 10 power 21 water molecule, all of them, they are oriented in the direction of the electric field. And like that, we are done with this example. I think it's so easy, just we have to know the definition of the work, the definition of the potential energy, the definition of the difference in the potential energy, the definition of the torque, the definition of moment dipole, and that's all. Let's move to the class activities. 3-point charges lie at the vertices of an equilateral triangle as shown. Charge 2 and charge 3 make up an electric dipole. 2 and 3 are an electric dipole. The net electric torque that the charge 1 exerts on the dipole is clockwise, counterclockwise, 0, not enough information to decide. Okay. When we talk about the torque, we have to think about the force, electric force. The force between charge 1 and charge 3, it's attractive because they have different sign. This is the force exerted by 1 on 3. The force exerted by 1 on 2, it's repulsive. F1 on 2. Now, in which direction this electric dipole will rotate? It will rotate clockwise. Okay. Let's move. 3 points of charge lie at the vertices of an equilateral triangle as shown. Charge 2 and charge 3 make up an electric dipole. The net electric force that the charge 1 exerts on the dipole is along the positive direction, along the negative x direction, positive y direction, negative y direction, none of the above. Please here don't be confused because we said the net electric force of an electric dipole in the presence of a uniform electric field is 0. Did we have a uniform electric field here? No, we don't have. We don't have a uniform electric field. So what will be the net force? At first, let's try to draw the force exerted by 1 on 3. So it's attractive, F1 on 3, and this is F1 on 2. It's repulsive because F1 on 2. So let's try to draw the two forces in the same point. This is F1 on 3, and this is F2 on F1 on 2. The sum of these two forces is along the positive y-axis, F net. Okay, good. So the correct answer is positive y-axis. Let's move here. Last question of this lecture. The figure shows for orientation of an electric dipole in an external electric field. Now we are talking about the external electric field. In this case, we can say that F net is 0. Okay, so in which orientation is the potential energy of the dipole is greatest? Is asking about the potential energy. What is the definition of the potential energy? We said it's minus P E cosine theta or cosine phi. Phi is what? Phi is the angle between P and E. So P is the same for all these dipoles. The same electric field for all these dipoles. Which one will determine the magnitude of the amount or the amount of the potential energy? It's phi, and this negative sign also. Okay, for 2 and 4. For 2 and 4. Both of them, they have the same cosine. The cosine is positive. Yes or no? Cosine phi is positive. So U in this case is negative because we have a negative sign. Now let's talk for 1 and 3. The cosine of phi is negative. Okay? So that means the potential energy is positive. What do you think about the cosine of these two angles? Yes, of course, it's the same. Why? If we draw the trigonometric circle, okay? These two angles, they have the same cosine, which is negative. These two angles, they have the same cosine, but it's positive. Okay, so what is the correct answer? To get positive, greatest, that means positive potential energy in the dipole 1 and 3. We have the greatest potential energy. Okay, so 1 and 3 is the correct answer. Thank you so much. This is our lecture for the electric dipole. As a summary, we can say that an electric dipole is a pair of electric charge of equal magnitude at opposite sign separated by distance d. The electric dipole moment is vector p, has a magnitude q multiplied by d, and pointing from the negative toward the positive charge. An electric dipole in the presence of an external electric field experiences a torque, which is equal P cross E, and the potential energy of the electric dipole in the presence of electric field is given by minus P dot E. Thank you so much, and see you in chapter 22.